Hello and namaste everyone. Welcome to lecture 2 of this course on stochastic approximation. Let us first do a quick recap of what we did in the previous class. In the previous class, we looked at the following problem, which involved estimating the mean of a random variable x using independent and identically distributed samples of the random variable x itself. We then came up with the online or incremental algorithm xn plus 1 equals xn plus alpha n times h of xn plus mn plus 1, where alpha n equaled 1 over n plus 1, and we referred to this alpha n as the step size. H of x equaled mu minus x, and we referred to this h function as the ideal update direction, and mn plus 1 equaled xn plus 1 minus mu, and we referred to mn plus 1 as the noise in the estimate of h of xn. So clearly h of x is unknown. It is unknown because mu is unknown. Recall that our goal is to actually estimate mu. So of course mu is unknown, and hence h of x is unknown for any x. However, if you add h of xn and mn plus 1, we get the quantity xn plus 1 minus xn, capital Xn plus 1 minus xn, and this quantity is indeed known at time step n once the sample xn plus 1 is available. So let me again summarize. We don't know h of xn because mu is unknown. However, we have access to the noisy estimate of h of xn, which is h of xn plus mn plus 1, and this noisy estimate becomes available when xn plus 1, which is the n plus first sample of the random variable x, becomes available, right? So now let's see if we can come up with a better interpretation of what this algorithm is trying to do, right? So let us define a function f given by f of x equals half of norm of x minus mu the whole square, right? So what we are imagining is that x is a d-dimensional random variable and f is a map from Rd to R, which is given by this update rule over here, right? Now in the previous slide we saw that h of x equals mu minus x, and this expression can be viewed as the negative of the gradient of this function f, which is given above, right? Thus h of xn plus mn plus 1 can be viewed as the negative of the gradient of f of xn plus mn plus 1. In other words, this noisy estimate of h of xn is actually a noisy estimate of the negative of the gradient of this function f itself. In other words, the update rule xn plus 1 equals xn plus alpha n capital Xn plus 1 minus xn, which was this h of xn plus mn plus 1, actually equals minus grad f of xn plus mn plus 1. Thus this update rule can actually be viewed as a stochastic gradient descent with regards to this function f. We say stochastic gradient descent because this negative of the gradient is not available because mu is unknown. Instead we have access to minus grad fxn plus mn plus 1, which can be viewed excuse me, which can be viewed as a noisy estimate of this negative gradient. Hence this update rule can be viewed as a stochastic gradient descent method, and if you recall my discussion from the first class, a stochastic gradient descent is actually a special case of a stochastic approximation algorithm. Alright, so in a sense the above example which involved estimating the mean of x was relatively easy because of two reasons. We wanted to estimate expected value of x, okay, so there is a random vector x and we wanted to estimate its mean, and we had presumed access to the samples of this random vector x itself. Okay, so in this sense this problem was easy, that we wanted to estimate something and we had access to the quantity of interest, right, direct access to the samples of the quantity of interest. However, in several real world applications it would be the case that we want to estimate expected value of x, that is the expected value of some random vector x. However, we do not have access to the samples of x. Instead, we only have access to the samples of a random vector y, which in some sense relates to x, right. So this is relatively difficult to the problem we saw in the first example. The difficulty is that we want to estimate expected value of x, but we don't have direct access to the samples of x. Instead, we have access to samples of another vector y, which in some sense relates to x. Such problem instances fall under the broad category of problems called as inverse problem. We will now look at one such example and examine how stochastic approximation or stochastic gradient descent can be useful in such scenarios as well. So this is example 2. Again, the purpose of this example is to illustrate the utility of stochastic approximation algorithms in applications of interest. So first let me give a simple verbal description of the problem that we plan to tackle under this example. The problem is that we have a web page and we wish to estimate the rate at which this web page changes. Okay, so let me elaborate a bit. Imagine your favorite web page. Maybe if you are interested in cricket, maybe there is this web page that displays scores and so on and so forth, right. Now as new information about cricket becomes available, the web page updates itself, right, and we would like to know when does this web page change. In particular, we would like to know the rate at which this web page changes. So what do I mean by that? You can consider any unit interval of time that is of interest to you. For example, you could consider 1 second, 1 minute or 1 hour, whatever works for you, and you would like to know how many times on an average does this web page change in this desired unit interval of time, right. Now one can ask, okay, why would one be interested in knowing the rate at which web page changes? Well, a simple motivating application would be in the context of what is called as a web crawler, right. So sure, in today's day and time, okay, one uses maybe the LLM such as ChatGPT or Gemini and so on and so forth to ask questions. However, a few years back we relied on search engines such as Google, Bing and so on and so forth, okay, to get answers to the questions that we may have had. So when I was young and I used a search engine, I was very surprised. I was surprised because whenever I used to type in a question, the search engines used to instantaneously provide answers to these questions, and I always used to wonder, wow, how can this search engine actually search so quickly and fetch the answer for me? Okay, so over a period of time I realized that these search engines do not actually search at real time. Instead what they do is they keep crawling different web pages. So by crawling I mean they keep visiting different web pages and checking whether the web page has changed or not, and if it has changed, download the latest information that is available to a local repository. And whenever a user actually provides a search query, the search engine doesn't search at that time. Instead it searches within the local repository and in some sense instantaneously provides an answer to this question. So you can see that if you wanted to design a web crawler, you would need to know the rate at which different web pages change, so that you can visit those pages at suitable intervals of time in order to fetch the latest information, right. So if you are interested in designing a web crawler, this question would be one of the fundamental questions of interest. So let me repeat this question again. The goal in this question is to estimate the rate at which a web page changes, right? So this is a verbal description. So now let us give a mathematical formulation, and since this is not the main topic of this course, I will keep the mathematical formulation of this question in some simplified way, but one can build upon this idea and look at more sophisticated versions of this question as well. Okay, so what is the mathematical formulation of this question? We have a web page, and we will presume that the times at which this web page changes forms what is called as a Poisson point process with rate lambda. Is that okay? So I will describe to you what a Poisson point process is, right? So you can see that the times at which the web page changes is some stochastic process, and one of the simplest stochastic process is what is called as a Poisson point process, and this Poisson point process is completely characterized by this single scalar variable lambda, right? And in some sense this dictates the rate at which the web page changes, and the goal of our problem is to estimate lambda, right? So before I discuss how we go about estimating this lambda, let me first try to explain what a Poisson point process means, right? A Poisson point process can be equivalently described as follows. Suppose Tn n greater than equal to 0. So this is a sequence of time instances, that is you have T0, T1, T2, T3 and so on and so forth, and for simplicity we will presume that T0 is 0. Okay, so suppose that this sequence of time instances denotes the times at which the web page changes. Okay, so we will say the sequence of time instances follows a Poisson point process if the interchange time instances, which is Tn plus 1 minus Tn. So if Tn is a real number, Tn plus 1 is a real number, then Tn plus 1 minus Tn will be another real number, and of course it goes without saying that these will be positive real numbers, right? So you look at T1 minus T0, then T2 minus T1, T3 minus T2 and so on, right? So you look at this sequence. We will say that this sequence Tn is a Poisson point process if the sequence of interchange time instances are independent and identically distributed sequence of exponential random variables with parameter lambda, right? So I will denote exponential random variables using the notation exp, and lambda over here denotes the rate of this exponential random variable. In other words, 1 over lambda is the expected value of this random variable, and you can already see that I have used this abbreviation IID to indicate independent and identically distributed. So this is a very common phrase. I am sure most of you must have already be aware of this, and I will be using this abbreviation quite often in this course. Okay, so please be aware of that. So let me summarize this slide. So we will say the times at which the web page changes forms the Poisson point process if the interchange times form a sequence of independent and identically distributed exponential random variables with parameter lambda. Okay, so what does the interchange times being exponential mean? It means that for each n greater than 0, Tn plus 1 minus Tn. So Tn plus 1 minus Tn is actually a random variable, and its distribution is like that of an exponential random variable with parameter lambda, which means that if you look at the tail CDF of Tn plus 1 minus Tn, tail CDF means if you look at the probability that Tn plus 1 minus Tn greater than equal to x, this would equal e raised to minus lambda x for all x greater than 0. Okay, so you can see that this lambda appears over here, and this lambda is the same lambda that you have over here, right? and if you are aware of a bit of Poisson point processes, then we can also say much more about this times at which the web page changes. For example, we can say that if you look at a interval a comma b of the non-negative real line, right, then the number of time instances that fall within AB, right, so which we denote by n of the interval AB. This is basically the number, okay. So the hash over here denotes cardinality, right, and this set includes all those time instances n such that Tn is between A and B, right, or Tn lies in the interval AB, and this interval I denote it as open from A side and closed at B side, but it doesn't matter because these exponential random variables are continuous, so it doesn't matter how I define these sets, but as per the standard notation I will work with such sets, that is open from the left and closed from the right. So if you let n of the interval AB be the number of time instances that lie in AB, then one can check that n of A comma B is actually a Poisson random variable with parameter lambda times B minus A, okay. So this lambda over here comes from this parameter lambda, and this B minus A is basically the size of the interval, okay. And when I say this is a Poisson random variable, what do I mean is that the probability that n of AB equals k, okay, this will equal this expression that is given over here, right. Alright, so this in some sense is a summary of the Poisson point process, and the name Poisson comes because of the fact that n of AB has this Poisson distribution, right. So let me now summarize what is the goal of this exercise, right. So clearly Tn's distribution, okay, is completely characterized by the single parameter lambda, right. So you can see that to define this Poisson point process I only need to specify this lambda, and once I specify this lambda, the interchange times have a specific distribution which is exponential with rate lambda, right. So that gets fixed, right, and our goal in this exercise is to estimate lambda, okay, that is the goal in this example, right. So now let us spend some time in understanding how this example differs from the previous example. So recall, in the previous example we had a random vector x and our goal was to estimate expected value of x, right, and we presumed access to samples of the random vector x itself, right. So here our goal is to estimate lambda, right, and let us first see how is lambda related to Tn plus 1 minus Tn, right. So as I said, lambda is the rate of these exponential random variables. Recall that Tn plus 1 minus Tn is exponential with rate lambda, which implies if you look at the expected value of Tn plus 1 minus Tn, then this will be 1 over lambda, right. So in some sense we want to estimate lambda, which can be equivalently posed as wanting to estimate 1 over lambda. So this then has a relation with the problem that we looked at in example 1, that is, if we had access to the values of T1 minus T0, T2 minus T1 and so on, right. So recall a few slides back I said that these interchange times are exponential with rate lambda. In other words, these are exponential with mean 1 over lambda. So if we want to estimate 1 over lambda and we had access to this T1 minus T0, T2 minus T1 and so on and so forth, then we could have used our SGD method from example 1 to estimate 1 over lambda, okay. And once we have 1 over lambda, you can invert that and get an estimate of lambda itself, right. So if we had access to T1 minus T0, T2 minus T1 and so on and so forth, we could have used the idea from the previous example. So recall that idea, it was computing xn plus 1 equals xn plus alpha n times capital Xn plus 1 minus Xn, right. So this is the sample of interest, and in this case what I will do is I will basically replace this by Tn plus 1 minus Tn, okay. Whatever is this value I will replace it over here, and one can then show that this algorithm, okay, will actually converge to the mean of this quantity over here, and the mean of this quantity we know is 1 over lambda. Hence one can show that this little xn's will actually converge to 1 over lambda. So if you run this algorithm for long enough, one can see that xn will give you an approximate estimate of 1 over lambda, and if you invert it you will get an estimate of lambda, which was the quantity of interest for us, right. However, in practice, right, such values, by such values I mean T1 minus T0, T2 minus T1 and so on and so forth, okay, they will often be inaccessible, right. And the question is, in such a scenario how can we estimate lambda? So the question that one can ask is, okay, if you cannot access T1 minus T0, T2 minus T1 and so on, what can we instead access, right. So this is like a practical difficulty. No web page may share the times at which it changes and so on and so forth, right. Instead we can get to know if a web page has changed or not between two successive web page accesses, okay. So this is a practical suggestion. So imagine you had a web crawler, it visited the web page at certain time instance. So it can download the current copy of that web page, and then it can visit that web page at some other future time instance, and at that time again it can download the later copy of that web page. So it has two copies of the web page, one that it had accessed previously and one that it accessed in the future time instance, right. Now this crawler or this software that you design can compare these two web pages and decide if the two copies differ, and based on that conclude that yes, between these two successive web page accesses the web page indeed has changed, right. So formally, if we denote Sn n greater than equal to 0 as the sequence of time instances at which we access the web page, right, then at time instance Sn plus 1 we will get to know if the web page is different from the copy that we had at time Sn, right. So this comparison we can do, and based on that we get to know whether the web page has changed or not, right. More formally, at time Sn plus 1 we get to know the value of the random variable In plus 1, okay. This random variable is 1 or 0. It is 1 if between Sn and Sn plus 1 there was at least one time instance where the web page changed, okay. So more formally, In plus 1 will equal 1 if n of Sn comma Sn plus 1, that is the number of changes in this interval Sn to Sn plus 1 was greater than equal to 1 and 0 otherwise, right. So what I am saying is that if the future copy and the previous copy do not differ from each other, then you can conclude that the web page has not changed. On the other hand, if the future copy and the previous copy differ, then one can conclude that yes, the web page has changed, right. So you can see that this value of In plus 1 is something that we can get hold of, and the question that we would like to ask is, given access to the values of In plus 1, right. When I say values of In plus 1, I mean given access to I1, I2, I3, I4 and so on and so forth, can we get hold of an estimate of lambda, right. Now the challenge with In plus 1 in some sense is that between two successive visits, right, if you sort of imagine this to be the timeline, and let's say you visited a web page at this time and you visited this web page again at Sn plus 1. Now in between these time instances the web page could have changed once, it could have changed twice, it could have changed 3 times, and so on and so forth. But this in plus 1 will not tell you how many times it has changed. Instead, it will only tell you if it has changed or not. So you can see that in plus 1 actually only gives you partial information about the web page change process, and using this partial information our goal is to estimate the value of lambda, right. So I will conclude this lecture at this point by summarizing what we have discussed, and in the next class we will discuss another stochastic approximation algorithm that makes use of the values of in plus 1 to get hold of an estimate of lambda. Okay, so let me summarize what we have discussed in this class. In the first class, in the beginning of this class, we showed that the example 1 that we considered, which involved estimating the mean of a random vector x using samples of x itself, that update rule that we came up with was basically a stochastic gradient descent, and we said that that problem instance was relatively easy because problem instance involved estimating expected value of x using samples of x itself. Then we said, okay, often in real life we may not be in such a good scenario. Instead we may want to estimate expected value of x using samples of another variable y that depends on x, right. And we saw an example of one such scenario wherein we wanted to estimate the rate at which the web page changes, but we only have access to these 0 1 random variables in plus 1, which doesn't tell you how many times the web page changes between 2 successive visits, but rather it only tells you whether the web page has changed or not between these successive visits. So in the next class we will see how we can make use of a stochastic approximation algorithm, use values of in plus 1 and come up with a way to estimate lambda. Thank you. Namaste.